Hello everybody, this is Jeff Janess and welcome to our second lab exercise on projections and datums. And in this lab exercise we're going to learn how to identify the coordinate systems of spatial data sets. We're going to learn how to calculate lengths and areas of polygons and polylines. We're going to learn how to project data into new coordinate systems, and we're going to learn how the length and areas of objects are affected by the coordinate system that they are in. All right, let's start up by adding these two feature classes to our map. And just for fun, I'm going to add a base map. You may do it with one of these that you like. I've always been partial to the USGS topo maps, and we learned how to add that in the lecture on data types. So if you're curious, you can go back to those lab exercises and see how to add this. Okay, first question. Both of these data sets that we just added, Trails and Eldon, they are projected. And what is the name of the coordinate system that they are in? Now there's a couple ways to find out, but we need to get to the layer properties to do it. So we can get to the layer properties by either right-clicking on the layer and going to Properties, or we can just double-click on it. Both of us will get there. Hit the Source tab, pop down to the Spatial Reference section, and here we go. Trails Dry Lake Hills is in NAD83 UTM Zone 12, and this is the projected coordinate system. If we scroll down, we see that this has a geographic coordinate system as well, and that means that UTM Zone 12 here, this projected coordinate system, was projected from this geographic coordinate system. So if the data set is projected, it will have information on both projected coordinate system and a geographic. And just to clarify this, if a data set does not have, if a data set is not projected, meaning that the coordinates are actually in latitude, longitude values, then it won't have any information about a projected coordinate system. And let's just quickly illustrate that. I happen to know that there is a data set in additional data in this geodatabase. I know that these three data sets happen to be all in geographic, so let's just throw one of these in and take a look at the coordinate system. All right, Source, come to Spatial Reference, and notice that there's only information about a geographic coordinate system. That's how you know that these data are not projected. Okay. So let's get rid of this. Okay, going through the lab exercise, we know the projected coordinate system. Well, we didn't actually check this one, but let's just check it real quick. Coordinate system is NAD83, so the same one, UTM Zone 12 projected from NAD83. Okay. Now we're going to calculate the lengths of the polylines in the trails, and we're going to calculate the area of the Eldon project. I'm going to fade this one out just a little bit so it's not quite so overwhelming. I like it as a background, but I don't like it just in my face quite so much. All right, so now we're going to calculate the lengths of the polylines and the area of the polygon. So first thing we have to do is open the attribute table, and we have to add a new attribute field. So let's open up the attribute field for trails. And you might notice I did that by right-clicking and going to Attribute Table. If you're comfortable with the keyboard, you can actually hit the Control key and the letter T. Control T will also open up a table. All right, so here's our attribute table for the trails. Let's step forward here. Okay. We're going to add an attribute field. To add the field, we need to have the little table tab open. There's the add field right here. Do that. It brings up this fields view. This just shows us all the attribute fields that are in this feature class. We're going to add a new one called length UTM. The data type will be double. That just means double precision. It's a term for the way a computer stores a number in memory. This is the method that uses the most amount of memory, so it allows it to store a number to the largest number of decimal places. It's basically the most accurate and precise way to store a number. So we're going to do that. We've got our new field added then. We're just going to save it. All right, the field has now been added. I'm going to close this fields view, come back to our table here. The new the new attribute field will be on the far right. Here it is. So now we're going to right click on it, go to, oh, there's no calculate geometry. You might notice that's disabled. When that happens, that means that the editor function is turned off. We need to turn on editing. So we hit the little edit tab, click the edit button here, and now we can calculate geometry. So we do that. In this case, we're going to calculate the length, that is this option, and we're going to calculate it in survey feet, and we're going to calculate it in the coordinate system of the data set. So we click Trails, Dry Lake Hills. It will automatically fill in UTM Zone 12. So this will give us the length in feet of every trail in UTM Zone 12 coordinates. Hit OK. And there they are. All right, so that gives us the length of those trails. Let's just pop forward here a page or two. Okay, now let's calculate the area of this polygon right here in UTM coordinates and in acres. Open up the attribute table. We're going to add a field. We're going to call this acres UTM. Again, it's going to be double precision. All right, we like our changes. We hit save. Now let's go to our table, scoot over here, right click and do calculate geometry. Okay, it's going to be acres. This is the attribute field we're calculating. Here we're calculating area, and we're going to calculate it in US survey acres. The coordinate system is going to be the coordinate system of the data. Eldon. The tool fills in UTM Zone 12 NAD 83 for us. We hit OK. And there we go. And you might notice that in this case it's the exact same value as this existing attribute field called GIS acres. And that's kind of nice to know. It sort of confirms what that data said. But I'd like to warn you that when you get data that has this type of attribute field that says like acres or GIS area or something like that, this is something that somebody has calculated in the past, and it may or may not be accurate. It could be that they calculated those attribute values, and then since then the data has been edited. Maybe this polygon has been cut in half or something, but the attribute value is still there. So you can't be positive that the acreage is still correct. That's why it's always a good idea to recalculate your own acreages. Okay. Let's scoot forward a little bit. All right, so next part of this lab, now we have learned how to identify the coordinate system of the data, and we've learned how to calculate lengths and areas in that coordinate system. So next I want to show you how to project data into a new coordinate system. We're going to take both of these and we're going to project it into the coordinate system called North American Albers Equal Area Conic. To do that, we have to use the tool called Project. So we hit the Analysis, we hit Tools, so it opens up our little toolbox. The projection tools are in the subset called Data Management Tools. Scroll down a little bit to Projections and Transformations. And the tool that projects vector data is here. So we click on that. We're going to project Trails, Dry Lake Hills. It is currently in UTM Zone 12 from NAD 83. We have to figure out a place to save it, and I'm just going to go with the default location here. It's in the default geodatabase. And we're going to call it Trails Albers. All right. Now I have to pick the coordinate system we're going to project it into. And we can search for it if you like. we hit this little button here. It opens up the coordinate system. The one we're looking for is in projected, it's in continental, it's in North America. Scroll down here a little bit, and it's this one. So we could click on that. I am going to try and help you guys through these labs. So all of these coordinate systems also have this thing called a well-known ID or WKID value. So I'm going to give you those numbers. You can just copy this, put it in the search button, paste it in there, and it'll find the coordinate system for you. So just a little bit quicker way of getting there. All right. Now, actually, while we're here, you might notice that we've got this coordinate system selected. If we hit the details and we take a look at the geographic coordinate system, it's also in NAD 83. So it's in the same geographic coordinate system as the original data set was. That's why we don't have to set a transformation. If they were from different geographic coordinate systems, we definitely would have to set a transformation. Okay, let's hit run, and it's going to go to work. Okay, it's added our feature class here, our new one. And now we're going to recalculate the lengths of those polylines. So open up the attribute table. We're going to add a new field. This time we're going to call the field length Albers. Again, it will be a double precision. By the way, if it had stayed as long is actually an integer format, so it would have no decimal values if you left it in long. Double is a much better numeric type for this type of value. All right, so we've added our attribute field. Let's save that. Close this. Come over to our new field, and we're going to recalculate the geometry again. It's going to be a length. It's going to be in survey feet. It's going to be in the coordinate system of trails, which is North America Albers equal area conic. Hit OK. Scoot over here. I'm just going to hide this for a second. Now notice they have the lengths in UTMs, that's left over from the last feature class, and now we have lengths in Albers, and they're fairly different. Looks like about 104 feet different in this particular line, just based on those two different coordinate systems, and that can be important. So yeah. One of the things I want you to think of as you're doing these lab exercises, there will come a time that you'll be responsible for managing some piece of land. You're going to have to decide maybe how many people to hire to do surveys on an area or to do timber inventory or something like that. And the size of the objects are going to be dependent on the coordinate system that you calculate the area in. And so if you pick a bad coordinate system, then it's going to give you very bad data. It could way overestimate the area or way underestimate. And in either case, it'll really mess you up as a manager. All right, so just keep that in mind as you do that. Always be thinking that you should choose a good coordinate system. All right, so we've done the trails. This lab exercise also shows us how to project the polygon. So let's do that real quick. Project. Now we're going to project the polygon. We're going to call this Albers. The coordinate system. This time we happen to have it in the layers, so we're just going to pick it here. No geographic transformation necessary. Hit run. It's going to make us a new feature class there. Let's open up the attribute table. Let's add a new field. This one we're going to call acres Albers. Double precision. Okay. Save our edits. Close the fields view. Come back over here. Recalculate the acreage using this new coordinate system. We're calculating area. The units will be survey acres. Coordinate system will be the data. And actually, we could have picked it out of here too. Eldon, Albers, yeah. Same thing. All right, hit OK. Calculate a new set of acreage. All right, let's hide these for a moment. So now we see the acreage has actually gone up a little. It's not too far off from what the UTM acreage was, but it is not the same for sure. Okay. Now, one last thing. Let's talk about geodesic links and areas. These are extremely cool new functions recently introduced into ArcGIS, which could solve a lot of problems we've historically had with projection distortion. I mentioned earlier it was really important to choose a good projection when we calculate areas and distances. This ought to be pretty obvious to you. If you have to plan out a survey area to inventory 100 acres of forest, you really don't want ArcGIS to tell you it's only 50 acres or even that it's 200 acres just because you picked a bad coordinate system. These incorrect acreage values will totally mess up the budget you plan for the inventory. It'll mess up the amount of people you hire and the time you allocate to complete the thing. Now, geodesic methods calculate the lengths and areas directly on the curved surface of the planet using spherical geometry on the latitude and longitude coordinates. It's considerably more complicated than calculating planar values from projected coordinates, and it probably explains why the function hadn't been available until recently. But it's available now, so let's try it out. Now this time I'm going to calculate the new sizes into our Albers feature classes that we've been working with before, this Eldon small project and trails, and we don't need to export these data into new feature classes just for this. Okay, so let's start by opening the attribute table. Let's add a new attribute field like we've done before. This time let's call it length geodesic. All right, it's a double precision. Save our edits. Come back to our table. Let's go over and calculate geometry once again. Now this time we're going to calculate the property length geodesic. Before we were calculating length, but now we'll do the geodesic. Like I said, this is going to calculate directly onto the surface of the planet. And in fact, because of that, the coordinate system really doesn't matter. No matter what coordinate system it is, the tool will project the individual features back onto the latitude-longitude system before it does the calculations. So coordinate system here does not matter. It's just going to go straight to the geographic coordinate system. Hit OK, wait for a sec. And there it is. So now we have, for this first line, the geodesic length is 6,900 feet compared to 6,897 in UTM coordinates and 7,001 in the Albers coordinate system. The geodesic length should be the most accurate. So this is usually the best choice to go with if you have to choose one. All right, so let's repeat that process with the small project polygon. Open the attribute table. We're going to add a field. This time we're going to call it acres geodesic. Double precision. There we go. Save the edits. Calculate geometry. Okay, we're going to calculate area in the geodesic property this time, as opposed to just normal area, geodesic. The survey units, or the areas, are going to be acres again. And coordinate system doesn't matter. Hit OK. And there we go. So, interesting to note here how close the geodesic area is to the Albers area. And I remember the Albers, that was an Albers equal area coordinate system. So the whole point of that coordinate system was that it would calculate areas accurately. So it's kind of cool to see that the most accurate method, this geodesic process, comes so close to the Albers equal area. Okay, everybody, one last step, and this one's pretty quick. Your homework asks you to calculate the cumulative area of some polygons, which means you have to add up all the values in the attribute field. And so I just want to show you how to do that. We're going to use what they call the statistics tool for this. Pretty easy to do. Okay, let's test it out on the Trails Albers feature class. Let's open that attribute table. We'll go back to our 3 new fields that we calculated. So these are our 3 lengths. Okay, we just right-click on the attribute field name length UTM, go to Statistics. It opens up our little chart window here, and it also opens up a separate pane of chart properties. So make sure you can find this pane. This is the one we're really going to use. If you can't find it, click the little Properties button here, and it'll bring it up. All right, so what we're looking for here is the sum. And this tells us that within the UTM coordinate system, the total length of all the trails is 231,677 feet. Now, to find out the total length in our Albers projection, all we have to do is switch this to the length Albers field, and we see that the total length has gone up a little bit. Now, the Geodesic method, the last one, remember this is the most accurate, has the length at 231,761 feet. All right, and that's the statistics tool. Really simple to use and quick to give you some good information. Okay, and it looks like that wraps it up. In this lab exercise, we started with looking at the coordinate system of existing data. I showed you how to project that data into new coordinate systems. We learned how to calculate the lengths and areas of polylines and polygons. And we learned that the different coordinate systems cause those sizes to be different. All right, thanks so much.